Hi, I'm just going to go through a couple of Hess cycle questions, just to recap a bit on your drawing of Hess cycles itself. So before you arrive here, I hope you have managed to recap some of your key concepts in chemical energetics. You should know what Hess law is, roughly the concept of a Hess cycle, and also there's this deck of Anki cards in the folder. Not sure if I'll be able to open it, but anyways, basically just a way for you to recap mostly all the definitions. Okay, wait, I don't think I can, but I can open it here. This includes the other part of the topic on entropy as well, Gibbs free energy, all that, which I'm not going to cover in this video. But yeah, you can see all your energetics definitions are all in here. Please know how to know exactly what these 9 definitions are in terms of the enthalpy changes, and also know your definition of entropy, know how to know exactly what the statement of Hess's law is, because although quite rare, they can actually ask you on that. So yeah, please know all your definitions here. Not sure why I can't open the Anki deck on my side. You might or might not be able to open it on your side, but anyway, yeah. And it's very important to, before you approach your head cycle, to please revise all your definitions. Um, and also please also note that first EA is you go from the gaseous atom to the singly charged ion. So singly charged means it's just plus. But the second IE, sorry, not EA, is you start from the unipositively charged ion and then you go to 2 plus. And third IE is from 2 plus to 3 plus and so on. So it's a similar concept for electron affinity, where in this case, first EA is you go from, let's say, oxygen, right? I go from oxygen gas to O minus. And then my second EA is not O to O2 minus. My second EA is O minus to O2 minus. So that's why we always write in the hair cycle first plus second IE, first plus second EA, because you need to add all these in order to make it uh the thing that you want. And also please also note all your electron affinities aren't in the data booklet, they will be provided to you. But the two important things that you need to get from the data booklet are section 2 here on your ionization energies, and also your section 3 here, bond energy. So all the bond energies that you will need and all the IEs that you will need are all here. Okay, anything else will be provided in the question now. So I think I've digressed quite a bit. Let's continue to the cycles themselves. So I'm going to skip your Hess cycles first. I'm going to go to Born-Haber cycle. So this in this case is 2024 Hwa Chong Promo paper 2. And I'm just going to take you through this question now. So basically, right, in your syllabus, there's actually not that many variations of Born-Haber cycle. There's a lot of variations of Hess cycle. But if they explicitly ask you to draw a Born-Haber cycle, then really the only Born-Haber cycle in your syllabus looks like this, okay? So this is the so-called standard Born-Haber cycle. And I say so-called because there's actually no non-standard Born-Haber cycle, at least for the purposes of your syllabus. So of course you need to label your axis, and I'm just going to use NaCl as an example because it's simple. Okay, so I always start, this is 0, okay, I must always start with the elements in their standard state. So if I want NaCl, right, this is my Born-Haber cycle for sodium chloride. I will start with sodium in its standard state and chlorine in its standard state. Now remember, when throughout this topic of energetics, and actually also in electrochem later, you need to state your state symbols. Okay? In this topic of energetics, unlike in most of your other topics, your coefficients for your chemical species are allowed to be fractions. In fact, a lot of the times they are required to be fractions for various working purposes. So this is going to be half chlorine, and chlorine in its standard state is a gas. So you start with the elements in their standard states first. And then, by the definition of enthalpy change of formation is you go from the standard state to the substance you want. So this is standard enthalpy change of formation. And I go to the substance I'm interested in, which is NaCl, solid. So this is an ionic solid. Now, to complete my standard Born-Haber cycle, I'm going to go to, no, that's a bit too high. I'm going to go to the next step, which is your standard enthalpy change of atomization. And that is going to be, I convert my element in a standard state to a gaseous atom. And then, once again, this Cl does not react. So anything that is unchanged, just copy over. Okay, this concept of anything that doesn't participate in this enthalpy change reaction, just copy over, will be very important later on when we're doing our two Hess cycle problems. Okay, next step in the standard Born-Haber cycle is going to be your bond is actually going to be the order doesn't really matter, but my personal preference is, since I've changed Na, I will continue to change Na. So if I want to change this to Na plus gaseous, and then my Cl is still unchanged, right? What's this going to be? This is going to be my first ionization energy of Na. So you can actually just put it up from the data booklet lah. It's just Na here. This is your first IE. So it's 494. But just know that it's first IE of Na. So now I have my cation in the gaseous state. Next, I need to have an anion in the gaseous state. Okay, so now I will focus on changing my Cl. So this one is unchanged. I just copy over. First thing I need to do, okay, is I have half Cl here, right? I want to convert this to just Cl. So just remember, right, these coefficients are just number of moles. So because bond energy is the energy needed to break 1 mole of a covalent bond, I only want to break half a mole of a covalent bond. So it's just half of the Cl-Cl bond energy. And Cl-Cl bond energy is just here lah, under homonuclear here, which is just 244. And final step in the standard Born-Haber cycle is final two steps actually. From here, up here, I want to do something else to the Cl, right? So before we continue and ponder what that could be, one thing that we haven't considered yet is our lattice energy. Because remember, this is an ionic solid. So lattice energy is obviously a term that comes to mind when we are talking about reactions involving an ionic solid. So let's go back to the definition of lattice energy, which is in my Anki cards. I'm just going to use this stack of cards to pull out our definitions now. So lattice energy is the heat evolved when 1 mole of solid ionic compound is formed from its constituent gaseous ions. So now that we have this definition in mind, now do you see why I must, in order to go from something to NaCl, this something must be gaseous. That's why this must be gas, this must be gas. Now from Cl to Cl minus, this is my, let's go by the definition. You'll see that this is simply my first electron affinity of Cl, which will be provided to you in the question if you ever need it, because it's not in the data booklet, so they have to provide it to you. So this is just a first electron affinity of Cl. So this is the standard Born-Haber cycle. And yeah, it's more or less the only Born-Haber cycle that you need to know. So in general, right, when they give you energetics questions, they can give you all sorts of 奇奇怪怪 combinations that are technically in your syllabus. By technically in your syllabus, right, I mean these definitions here, these 9 definitions, are the definitions, or rather are the enthalpy changes that you need to know within your syllabus LOs. So more or less any reaction scheme, any Hess cycle that involves one or more of these 9 different types of enthalpy changes, right, they can potentially ask you. So basically for Born-Haber cycle, okay, if you start to see any of these, okay, because a lot of the times the question will not specifically ask you to draw a Born-Haber cycle. If they just say construct an energy cycle, or if they say determine the something something something, then whether you draw Hess cycle or Born-Haber cycle is up to you. But if they tell you to directly construct a Hess cycle or directly instruct you to construct a Born-Haber cycle, then you have to obey by the instruction lah. What I'm trying to say here is that if you see these enthalpy changes in the information that they give to you. How do you know if if they don't ask you because in fact all the three questions here they actually don't ask you, they just ask you to calculate. So this one, how do I know that it's Born-Haber cycle, or rather how do I know that a Born-Haber cycle will be easier? Basically anything that involves lattice energy usually is Born-Haber cycle. I say usually because later we'll see a question where Born-Haber cycle is not the easiest way to do it. Okay, but you can see that there are a lot of things here in the standard Born-Haber cycle. I have Le, I have H atom, I have electron affinities. So the moment you see all of these very familiar looking enthalpy changes, then you already know, probably I should be drawing a Born-Haber cycle. Okay, so let's go into the question proper. I'm sorry if I spent 10 minutes talking irrelevant bullshit. If you have skipped all the way up to here because you just want to hear my explanation, totally valid. Anyway, let us look at this, okay? So I'm going to set up my standard Born-Haber cycle now. So, of course, I'm going to need to label my axis with energy, kilojoules per mole. And once again, just like the standard Born-Haber cycle, remember, start from the elements in their standard states. So elements in their standard states have a relative enthalpy of 0. So in this case, I want to construct a Born-Haber cycle for Al2O3. So in this case, they want us to find enthalpy change of formation, right? So we can put down here Al2O3 solid. And I want to find this enthalpy change of formation. Please don't just memorize the standard Born-Haber cycle, also be able to appreciate, okay, based on the definitions of the enthalpy changes. Everything about Hess cycle, Born-Haber cycle is all about going back to the definition. So I want to form from elements in their standard state. So what's my standard state? This is going to be Al solid plus 3 oxygens. Correct? No, 3/2. Yeah, sorry about that. Yeah, so this is from a standard state to a substance, my enthalpy change of formation. This is what I'm interested in. Now I'm going to work upwards and continue to construct my cycle. Okay, so next step. I want to, remember, change the metal first, right? So next step is just going to be, I want to go from solid to gaseous atom. And then this one, O2, or rather the oxygen is not changed, so just copy over. And this is going to be my enthalpy change of atomization of aluminium. So make it a good practice, right? Every time you have used a value in this table, just take it off to know that I have used the value. And make sure that you have used all the values. So this is going to be plus 326. But no, look at the coefficients. Okay, this is a learning point now. Earlier on, I used NaCl to illustrate the Born-Haber cycle for simplicity, but now things are not so simple. Okay, over here, I have 2Al, so I have 2 moles of aluminum. Because remember, all my energetics definitions is the energy needed or the enthalpy change when 1 mole of something reacts. Now 2 moles of this something are reacting, so I need to multiply by 2 times H atom. Then only I can come here. Okay, so this one is done. I have used it. Next, I want to go from, remember, just keep changing the metal. So now I want to go from my ultimate goal once I get up here. Just a reminder, my ultimate goal is to get up here and get my gaseous ions. So my gaseous ions are going to be, I need 2 moles of gaseous Al3 plus 3 moles of gaseous O2 minus. So I've already changed everything to the gas, right? This is gas, this is gas. So for the rest of my cycle, I no longer need to change state symbols. But I need to get from Al to Al3 plus. So I'm going to do that now. I change it to Al3 plus. Once again, oxygen, nothing happens with the oxygen. So just copy over. And obviously, this is going to need to be uh my first ionization energy plus second IE plus third IE. Once again, I mentioned right at the start of this video, right? Please do not just copy the third IE. You need first plus second plus third. So we're going to go to our data booklet now. Under aluminum, first IE is here, second IE is here, third IE is here. So it's 577 plus 1820 plus 2740. Let's punch calculator for a bit. So that's going to be 5137. So I need two moles of this. 2 times I added those three together and I said it's 5137. But actually for my working purposes, just to show you so that we are clear, this is first IE plus second IE plus 2740, third IE. Okay. And then next, I can focus on changing my O2 now, right? So I want to get from O2 to O2 minus. So I have two steps to do that. The first thing I need to do is I want to go from 3/2 O2 to 3O. So in order to do that, I am going to want to take actually 3/2 of the OO bond length, right? Because if I just want to take one of the OO bond length, it's just O2 to 2O. But in this case, I have 3/2 moles of O2. That's why I need to have this 3/2 over here. Okay, so please don't take out the wrong coefficient. Just take out whatever coefficient is here. This coefficient here is going to be this coefficient here. Okay, so we go to our data booklet. OO bond length, if I bond energy is 496. Yeah, quite easy to remember after you've worked with it for a bit. Uh, Actually, it's also good practice to put the plus lah at the front of every enthalpy change. It's not needed for your rough working. Your rough working, actually, you don't need to follow the conventions of, oh, always must state units lah, always must state sign lah. But it is good practice to get into the habit so that you don't forget to state the uh plus minus and the units in your final answer. Okay? And then to go from here to here, I'm going to want to use my electron affinity. So we can come here, my first electron affinity and my second electron affinity. So I'm going to use both of these now. And you can see that my first electron affinity is -142 and my second is +844. So once again, I have 3 moles of this. So I'm going to want to -142 plus, plus 844. And then finally, my lattice energy, which I'm going to use now, is, let's go back to the definition, check that it's correct. I go from my gaseous ions to my solid ionic compound. Yes, so this is -15451. So punch your calculator, you should be able to get this answer for HF. But just to show you again, as a general rule of thumb, when you are doing energy cycles, please know that when you are going in the direction of the arrow, you use the sign that is given. If you are going against the direction of the arrow, then you need to flip the sign. So in this case, that's the other thing I love about Born-Haber cycle. You notice, right, your Born-Haber cycle, especially for Born-Haber cycles that ask you to find HF, there are no arrows that you need to go against. It's just by Hess's law, the enthalpy change is the same whether I go like that. You try to follow my red cursor, okay? My enthalpy change is the same whether I try to go like that or whether I try to go one whole way round like that. Okay, you can see my cursor. Good. So actually I think I'll make my pen a bit thicker so that you can see. Is that better? Yeah, that's better. So yeah, whether you go like that or whether you go like that, is the same enthalpy change. So in this case, HF is just equals to like that, like that, like that, like that, like that, minus 15451. Okay, can? So yeah, just check that you have that answer. And we're going to move on now to more two slightly complex energy cycles. I think I'm just going to do this one first. So this was from 2023 promo, and in the original question paper, they actually you can see how synoptic questions can be also lah, because they started this question by asking you about theories of acids and bases. Then only they go into energetics. Just a reminder, I'm not covering this in the videos in depth, but just a reminder, calorimetry is Q equals to MC delta T. You need to know that. And also very important for practical. Okay? So I'm not going to go through that. I'm also not going to go through this because this one is really just using bond energy data to calculate your enthalpy change of reaction, which you more or less did in Sec 4 already. So I'm going to go through this part of the question. Question 2B part 2 of 2023 propo. And yeah, I'm just going to give you the delta H3 that they ask you to find in B part 1 is just minus 135. So key lesson throughout these two Hess cycles is as follows. Okay, as I mentioned earlier when we were doing Born-Haber cycles, firstly, anything that does not react, in other words, anything that is unchanged, just copy over. This is first lesson. Second lesson, okay, you need to know how to add new species on both sides to balance. And I don't think there's any better way to show you how to apply these two key skills in Hess cycle except by showing you these two Hess cycle examples. Okay, so first thing you need to do is, let's see this, okay? I want to find the enthalpy change for reaction 4. So third key skill, this is perhaps the most important one that I want to emphasize, which is that please it is a lot easier to start your Hess cycle with the equation of the reaction you want on top. Okay? Why is this the case? I be honest, I have no idea why lah, but it's just that it's something that we have been taught for generations. And from personal experience, it's a lot easier as well to start with what you want at the top. Because if you start with something that you are given, then it's not very easy to be able to find like where exactly do I slot in this reaction for. Okay, so I'm going to start with this at the top. Okay, so I'm given NH4Cl. Remember your state symbols at all times in energetics. So don't be lazy to copy your state symbols. And I want to find this standard enthalpy change of reaction. So I'm going to use this question mainly to teach you the second skill over here, the skill of adding new species on both sides to patterns. So the first thing, this is a tricky question, and what makes this question so hard is the fact that if you look at this, right, you can't think of exactly where to so-called insert these 4 pieces of information that you are given. So you want to find this, but then they give you 4 pieces of information, right? Let's just color code them. 1, 2, 3, 4. So they give you these 4 pieces of information. You're not entirely sure where to slot them in. But fear not, okay? Just as for organic synthesis, Hess cycle is also similar in the sense that you don't always need to work from left to right. You can also work from right to left. Unlike in math and unlike in organic synthesis, it is not only possible and feasible, but in fact recommended to work simultaneously from the left and from the right. What do I mean, right? Let's try to work from the left first, okay? How can I go from here? So you might be thinking, okay, I'm given a couple of things I have. Enthalpy change of neutralization, formation, reaction, all that. Okay, so let us try to start with the first row of the table, okay? Let's say I want NaOH and HCl, but there isn't a HCl on this side. But you see, I can just add. I can just add a HCl to both sides to make it balance. So this may sound a bit illegal to you, but trust me, it's perfectly feasible. Actually, no, let me put this in a different color. So I'm going to use red, okay, to denote anything that I add on both sides. So I'm going to add HCl, AQ on both sides so that it's still balanced. And this is analogous to a lot of methods that you use in math as well, lah. If an expression doesn't look like what you want it to look like, you can add something on both sides or multiply it by 1, and somehow it'll look nicer. I mean, my math is pretty bad, so I'm not sure how that works. Anyway, NaOH and HCl, they undergo neutralization, right? So they are going to form NaCl aqueous, remember your state symbols, plus H2O liquid. And just remember as well, anything that does not react, you just copy over. So the NH4Cl is unchanged, just copy over along with the state symbol. And this is minus 57.3. So this one and this one has undergone neutralization to form this. Okay, let's just give a tick. We have used this piece of information. Next thing I can think about is how exactly do I get here? Because think about it, right? What do I have in common between two of the pieces of information that I'm given? I'm given enthalpy change of formation of NH4Cl. Once again, what's enthalpy change of formation? I go for my elements in their standard states to the substance that I want. And the elements in the standard states for NH4Cl are going to be 2H2, half N2, and half Cl2. And where do I find that? Half N2 plus 2H2 plus half Cl2 is also given in the third piece of information here. So what if, right? What if I want to form NH4Cl, right? I want to form this, right? So I have half N2. Remember your state symbols. I copy over all my elements in their standard states. Perfect. And then what do I have? My NaCl and H2O here, right? So anything that does not react, once again, just copy over. Okay. And standard enthalpy change of formation of NH4Cl is minus 314 minus 314.6. So let's give it a tick. We have used this piece of information now as well. Now, I'm going to work from, looks like I'm stuck working from the left. So let's just start to work from the right now, okay? But before I move on, once again, please note the direction of your arrow. Your arrows don't need to all point neatly in the same direction. Make sure your arrows are pointing in the correct direction, okay? So let's go from here now. I am given in the question another piece of information regarding this species, right? HClAQ. And I'm given that the enthalpy change of reaction from gaseous to aqueous HCl is this particular value. So copy over anything that does not react. So I copy this entire chunk here. And then this is, I want HCl gas here, right? That only when it reacts with an enthalpy change of minus 74.8, that only can give me HClAQ. So I have used this. So we only have one last piece of information. And you see where this fits in now, okay? Half N2 plus 2H2 plus half Cl2. In other words, this entire chunk, I want it to form NH3 plus HCl. So this means that NaCl and H2O you should just copy over, right? Well, look what we've got. NaCl and H2O are here. They don't react in this reaction. So you see how my cycle is nice and complete now. It is minus 135. So my Hess cycle is complete. Now there's only one thing left to do, which is to press calculator. So I'm going to show you how to press calculator properly, okay? So remember, my Hess cycle, ultimate idea of a Hess cycle is that whether I go by this, sorry, ultimately whether I go by this way or whether I go one big round around, my enthalpy change is the same. So I'm going to want to go like that, then like that, then like that, then like that. Okay? But please take note of the direction. So I'm going to show you how to press calculator properly now, okay? So I don't have enough space on the bottom. I'm just going to go to the side here. My enthalpy change of reaction is going to be, follow the direction, right? Minus 57.3. But then here, my arrow is pointing from bottom to top. I am trying to trace from top to bottom. So because I'm going against the direction of the arrow, I need to flip the sign. So instead of negative 314.6, this one become plus 314.6. Okay, this is very important. If you need to pause, go back to what I just said, come back here. Okay, and understand that when you go against the direction of the arrow, you need to flip the sign. And then these two, quite simple lah. These two, I'm just following the direction, so don't need to flip sign. Just copy over. And if you press calculator, that should give you your answer of plus 47.5 kilojoules per mole. Remember, must have my sign, must have my units. Akan datang. Okay? So, I think we are going to go on to the last bit now. I'm going to pause this recording for a bit because I need to take a break, and you can also pause and take a break to consolidate what we've just learned before we move on to the last question. Okay, so we are now last question, and I want to determine the standard enthalpy change of formation. So this from 2025 Hess promo, right, was quite an interesting question because some people say, I have lattice energy, I have enthalpy change of formation, atomization, I should use Born-Haber cycle, right? Actually, this was actually my year's promo paper lah in 2025. Actually, when I first saw this question, I also thought, I should be using Born-Haber cycle, and I did use a Born-Haber cycle. Spoiler alert, in the end, I actually did get this question right lah in the exam. But basically, instead of 4 out of 4, I only got 3 out of 4 because my presentation was all over the place. So I'm going to show you the Hess cycle method that ensures that your presentation is neat and correct and proper so that you don't get minus marks like me. By the way, there is actually presentation marks in chem, just like in math. Or should I say, you won't get plus marks if you write very neatly. But if the way in which you present your information is in such a way that the examiner cannot tell convincingly that you actually have constructed a coherent Hess cycle that makes sense, or if you combine too many arrows, if you jumble too many steps together like I did in this exam, then yeah, you will minus marks. Because what I did when I first did this question, right, is I don't know what was going through my head, but somehow I combined so many steps in my Born-Haber cycle that I ended up having like 3 different enthalpy changes all on one arrow. Until I had to write an asterisk there and write at the bottom of the page, note to the examiner, this is what I mean. But unfortunately, that is not a way to show your examiner that you know what you're doing. Okay, they are not obligated to read any of your special footnotes in the exam. So please don't do what I did. Lesson learned. Okay. As you have probably been able to tell from Born-Haber cycle, if you do intend to construct a Born-Haber cycle for this question, and it's possible, you can go and try if you want. Anything that is positive will point upwards. Anything that is negative will point downwards. Hess cycle, it doesn't matter, as you can see, whether I point upwards or downwards. So in this case for Hess cycle, I'm not gonna harp too much on the direction of your arrows or even the direction of your cycle. It doesn't matter. But if you intend to approach this question from a Born-Haber cycle, you can, there is a way, and you have to make sure that you don't do what I did and make sure that all your arrows point correctly. Yeah, another mistake that I did that got me minus marks was I think I pointed up for a negative enthalpy change. So the marker, who was Mr. Wee Chong Shin, by the way, he didn't really like that. Yeah, so enough about the stupid mistakes that I made. Let's go on to how to do this correctly using the recommended Hess cycle method. By recommended, I mean because this is actually the Hess cycle method that was given in the teaching solutions to this question. So this is how the examiners or the setters for this question preferred candidates to answer. Now, remember, once again, like the previous Hess cycle, we are going to start with what we want on top, correct? So what is it that we want? I want the standard enthalpy change of formation of HF2 minus. Now, this question not as kind as the previous question lah. They never give you the equation that you want, so you need to construct it yourself. By the way, typo here. Yeah, that's a very ugly way to fix a typo, but never mind. So you need to construct the equation for the standard enthalpy change of formation yourself. So that is going to be I go from my standard state. So my standard states, I have half hydrogen gas plus fluorine gas. I'm interested in finding this. This is my unknown standard, so I must have this not symbol. And I get HF2 minus AQ. Obviously, ion is AQ. Actually, no, not obviously. Can also be gas. Ignore what I just said. Anyway, so at this point, it's easy to get stuck because you might think, how exactly can I go from here? They gave me Na in addition to HF2. So remember the method that we employed earlier. When in doubt, right, if you need to balance, you can just add something on both sides to balance. So I can add Na plus aqueous on both sides. Why do I add Na plus aqueous? Why don't I add Na plus gas? Very good question. You will see why in a bit as I continue to work. Okay? So in the event that you were stuck on this question, I'm telling you, giving you a hint, this is the first step. Hopefully, once I've given you this step, if you want to attempt the question on your own before you listen to my explanation, you can continue to work through this on your own. Final answer is minus 519. Okay? So if you want to pause the video here, using the hint that I've just given you to work on your own, you can work on your own. Okay? Now let's go through how to do it. Okay? So, remember, I have multiple pieces of information, right? There's unfortunately too many things for me to color, so I'm just going to not color for this question. Okay, so next step from here is to actually look at which pieces of information we can use. So because I have one ion in an aqueous state and one ion in a gaseous state, there's nothing I can do about the solution or the hydration or the lattice energy. So this one and this one we know we cannot use. And we also cannot use atomization because atomization is Na solid to Na gas. So these are not the ones we should be using. So I do not want to use this. I do not want to use this. I do not want to use this for now. Okay, so should I be using this one or this one? You should see that I should be using this one, right? Because if I use this piece of information, I have minus 481 here, right? So from half H2 and F2, I'm going to get HF2 minus gaseous. And this Na plus does not react. So anything that does not react, you copy over. So I have used this piece of information. Done. Now, 4 more pieces of information that we are supposed to use, okay? Now, if I want to go on from here, remember I said earlier, you can work from left to right or from right to left or both at the same time. So, what if I want to try to work on this side now? I can, right? Think. because my arrow can point both towards the thing that I want and away from the thing that I want, don't always be trying to think about what can I get from here. You can also think about what can I do to get to here. And this dual method of thinking, sometimes you need to consider both at the same time. It's also very, very important in organic synthesis. Okay, so how can I get to HF2 AQ and Na plus AQ? Think about it, right? I can actually get here from my ionic solid NaHF2. And you'll see that this corresponds nicely with the definition of enthalpy change of solution. You understand how this corresponds to the definition? You understand why this is correct? I hope you do. Okay, good. Next. Once again, don't just think about how can I get away from here? How can I get to here? Obviously, we associate ionic solid also with its lattice energy. We encountered in the Born-Haber cycle earlier. How to do this? And the lattice energy, which we're now going to use, is minus 825. So do you see how, now that I've unstuck myself by working from the right as well, I have used another two pieces of information. So there are only two more pieces of information that they want me to find. Correct? Sorry, only two more pieces of information that they want me to use. So I can continue to work from here or I can work from here. Once again, over here, don't just think about how I can go away from here. Think about what I can do to get to here. How can I get a aqueous cation? Wait, I'm so sorry. I think I might have spotted a mistake in my own working. Okay, wait. This solution that I have scribbled down for myself, I'm actually not sure how I'm correct. I will try to talk it out with you and hopefully discover where my own mistake was. Anyway, let's focus on this arrow first. This one, obviously, you can use this. No, it's not obvious. In order to get from Na gas to Na plus gas, so I start from nothing, no charge, to one charge, keep it in the gaseous state. My HF2 minus gas does not react. This is going to be my ionization energy. Let's go to the data booklet. Oh shit. Data booklet. Ionization energy of Na. Na, where's my Na? 494. First ionization energy. So this is going to be plus 494. I've obtained this from the data booklet. So there are still two more pieces of information that they want us to use. One is standard enthalpy change of atomization. One is standard enthalpy change of formation of Na plus. Oh, okay, yeah, then I'm not wrong. Because remember, standard enthalpy change of formation is I go from the standard state to the substance. So my standard enthalpy change of formation is just minus 240. And the HF2 minus does not react, so just copy it over. How did I write F as 4? Okay, and lastly, last piece of information, standard enthalpy change of atomization. So once again, I go from standard state to gaseous. This is enthalpy change of atomization. Done. So HF, I'm just going to trace, right? So once again, just like the previous one, anything that is in the direction of the arrow, I keep. Anything that is against the direction of the arrow, I must flip side. So this one is in the direction. This one is in the direction. This one is against the direction, so I must flip. So this is going to be minus 481 plus 240. I must flip this minus to a plus because I'm going against this arrow. So minus 481 plus 240 plus 107 plus that. Key all that in, you should get minus 519. Okay, this has been a bit of a long video. Other than myself who has watched this video in its entirety, I'll be quite surprised. So yeah, thank you for being with me, and I hope you have gained a better understanding of how to draw Born-Haber and Hess cycle. And of course, there are a lot of other aspects in this topic on chemical energetics as well. Most pertinently, the last unit on Gibbs free energy change and entropy, which I'm not going to do a video on because I don't see a point. So yeah, hope these three questions have allowed you to gain a better understanding of Hess cycle and also these key techniques on how to make your life easier. Okay, and remember, just because it looks like a Born-Haber cycle question doesn't mean a Born-Haber cycle is always the way to go. Okay, only draw a Born-Haber cycle if you're entirely sure that you can fit it within this so-called standard Born-Haber cycle. Can? Okay, thank you, bye-bye.